So I want to talk about, at least start with neutron scattering, but that's going to lead to something called the dynamic structure factor, which has a lot of important and interesting, very important and interesting properties in its own right. So although we're going to use the neutron scattering as a beginning, we'll end up talking about at least a lot of other properties of this particular rather complicated function. The nice thing about neutrons is that they typically are cold. The thermal energy is, let's see, 10 K degrees, which is equivalent to roughly 10 millielectron volts, because if you remember, room temperature is a 40th of an electron volt. And the wave number, lambda thermal, the de Broglie wave number is about 10 to the minus 10 meters. So this is a very convenient wavelength because this is just comparable with the interatomic spacing. And so neutrons are nice because by changing the energy, you can vary this thermal wavelength with the square root of the temperature. So you moderate them. These are cold neutrons that come out of a reactor. You get a whole hot neutrons, and then you moderate them and cool them down until you get to these temperatures. The details, I have no idea how they do it, but it's the magic of science that they know how to do it. So the question is, how does a neutron interact with an atom? Basically, the electrons are invisible because they don't have any baryon charge, and the neutrons are neutral. So there's a very weak scattering because of the magnetic moments, but that's irrelevant from our purposes. So the neutron really interacts with the nucleus. And this is an idea that goes way back to Fermi in the 1930s, that you can approximate, if you're willing to just do Born approximation, you can approximate the interaction of a neutron, V of a neutron at R with an atom at capital R, as you get this so-called Fermi pseudopotential scattering length. You write this as 4 pi h bar squared a sub s over twice the mass of a neutron. And here I'm assuming that the nucleus is heavy and doesn't recoil. Many of you have seen this formula in the BEC, and really what you say is this should be 1 over twice the reduced mass, where 1 over m sub r is 1 over m1 plus 1 over m2. This is the usual formula for the reduced mass. And here we're saying that the mass of the nucleus is heavy compared to the mass of the neutron. If you have two identical bosons, then the factor of 2 goes away, and this is the mass of the boson. And this is the formula with a single factor of 1 instead of 2 that many of you are familiar with in connection with the BEC. And the other important factor is this is short range, and you write it as delta of R minus capital R. So this is a three-dimensional delta function. It's a short range. It's called a pseudopotential. It doesn't make sense to try to do perturbation theory in this. If you try to iterate it, you get nonsense because you end up with squares of delta functions. And so Fermi's beautiful idea is that if you use Born approximation and you put in the exact scattering length, you get the exact answer. It's a typical Fermi sort of elegant physics idea that allows people to do these rather complicated computations. Question, Chris?
Is it S wave because the neutrons are so cold? S waves.
I think that's the right answer. I think there's factors of P wave scattering would involve factors of, well, it would be, I'd have to think about the factors, but if you look at the expansion of the scattering amplitude, you get S wave is the leading term, and then you get a factor of k times the P wave and k squared times the, and because the wavelength is so small, I think you're always in the long wavelength limit. So you can neglect the high, you can always neglect the other terms. Now, there may be cases where the S wave scattering vanishes. I mean, you can't really calculate the scattering length for nucleons off neutrons. At least you can't do it accurately, so I think it's usually just measured. Question?
Since the potential is a delta function, only the zero impact parameter counts. So then that's wave.
Right, but I mean, if you wrote down a p wave, you get something like, in momentum space, you get a factor of k, which is like a gradient. So I guess in physical space, you get delta prime. You get derivatives of a delta function if you did the p wave case. I haven't thought about it. So what you'd work it out in momentum space and then transfer back to this kind of. They actually do this in the interaction between in the dilute Fermi gas trapped. You only have a single species, and so you have the Pauli exclusion principle forbids the S-wave scattering, and so you have to go to P-wave scattering. And I've never actually studied that. I don't know whether they treat that in momentum space or whether they treat it in position space. But if you do it in position space, it must be the gradient of a delta function or something like that. But as I say, I haven't thought about it.
Yeah.
This is all we're going to need, and this is now, if you have a whole assembly of atoms, then the total interaction, V external, which interacts with this, is just sum on J equals 1 to n for n atoms, V of R minus Rj. Okay? And the only J dependence is here. So this is just 4 pi AS h bar squared over twice the mass of the neutron. And you get the sum of delta functions. And the sum of delta functions is exactly what we call the number density. So this couples to n of R, where n of R is just the sum of these delta functions over all the different atoms in the system. And so the reason this is so powerful is the interaction potential of a neutron with a many-body system is just directly proportional to this factor, and then it couples directly to the atomic density, because every atom has a nucleus, and it couples to the nucleus. It doesn't see the electrons, it just sees the nuclear, which is basically little points. And so you can study the details of the behavior of the local density as you carry this out. And so now we're going to have a little picture of a target. We have an incident neutron, and the incident neutron will have a wave number k and a spin projection lambda. So this refers to the neutron. This is it goes out like this. This is the target. We get a k prime lambda prime, where this is the final momentum, and this is the spin projection of the final neutron, lambda prime. And then the target goes from some initial state I to some final state F. So in this process, we're going to have a transition from some initial state I of the target, and the neutron properties k lambda, and after the scattering, we have the target is in a final state F, and we have k prime lambda prime. So now we're just going to do basic quantum mechanics. And the neutron wave function is, let me write it, psi k lambda for the neutron is 1 over the square root of v, taking a box normalization, e to the I k dot r. And then we get a neutron spinner a to lambda, where this is a two-component thing which tells us about the spin state of the neutron. If you use up and down, this would be 1 and 0 and 0, 1. But it could be anything. They could be polarized in any direction. We're going to average over them because you don't really measure them. But to get the factors right, you've got to be careful about all these different states. Okay? And so, in order to study this transition, we need to go from, we want to study the matrix element, FHI, this is the matrix element that we're interested in, because eventually the square of this is going to determine the rate using Fermi's golden rule. And so this is just putting all these factors together. You get a 1 over v because you get two factors of this wave function. You get an integral dv prime, integral over the volume. You get e to the minus I k prime dot r. You get eta lambda prime adjoint. This is the neutron. This is the final neutron spinner. You get f v external I. And then you get the neutron state here, eta lambda e to the I k dot r. Can you all see that? Is this in the way? I'll try to be careful. Now, I'm going to make some assumptions. I'm going to assume the interaction is spin independent. Sometimes that's not true, but that's the simplest approximation. And so I just get eta lambda prime adjoint times eta lambda, the product of spinors, which gives me a Kronecker delta in the two. So if the neutron interaction is spin independent, then you just get a Kronecker delta in the two lambda indices. And that's an assumption I'm going to make. So let me erase this and try to use the upper part of the board. In fact, I guess in my notes I called this HFI. And let me just call it that because that's what I wrote down here, is I get delta lambda prime over the volume. I get 4 pi a sub s h bar squared over twice the mass of the neutron. Now I get an integral dv prime e to the minus I k prime dot r. Times, I get the final state of the target, this is just n of r, I, and then I get e to the I k dot r. Now, if you remember, we called q is k minus k prime. So what we really have is delta lambda prime over the volume, 4 pi a sub s h bar squared over twice the mass of the neutron. And this is just the Fourier transform of the density. So this is really just the matrix element of f n of q I. Now, to be careful, this is Fn adjoint because of the way we define the Fourier transforms. And so you can think of this as saying you take the initial state of the target, you create a density fluctuation of wave number q, and that has to have an overlap with the final state. So only final states that differ by momentum q, you go from I, you add momentum q because this is a creation operator, or this is n of minus q, which is quantum mechanically a creation operator, and then you have to have a final state that has momentum, which is q bigger than that of the initial state. Okay? So this is a very nice physical picture that the excited state that the neutron creates, you take whatever initial state you have and you create a density fluctuation of wave number q. And so the excited state, if you start with if I happens to be the ground state, then this would be a first excited state which has wave number q. But we're eventually going to do a thermal average over all initial states and sum over final states. So there's a lot of manipulation that we have to go through in order to get the answer. But I mean, it's a really elegant application of Feynman's golden rule. And it's one of those things that you all know about, but you may not have actually seen worked out in such gory detail. So I like this example. So now the golden rule, Fermi, says if you want to go from an initial state I, k, lambda to a final state f, k prime, lambda prime, what you need to do is take this matrix element, square it, you multiply by a factor of 2 pi over h bar, which just comes from Fermi's computation, and then you have an energy conserving delta function. So this should be familiar. that the rate, this is called the transition rate, is just 2 pi over h bar, the matrix element F, k prime lambda prime, V external, I k lambda squared. It's the square of the matrix element. And then you have this factor, which is the energy conserving delta function, delta of h bar omega minus EF plus EI. Okay? Now, this is the difference of the target energies. And it says that the energy gained by the target has got to equal the energy lost by the neutron. And so h bar omega is just h bar squared k prime squared over twice the mass of the neutron minus h bar squared k squared over twice the mass of the neutron. And this is the energy that's lost by the neutron, or the energy that's gained by the target. And the reason this is so powerful experimentally is that we can experimentally measure the velocity of the neutrons. These are non-relativistic neutrons. And you can measure their speed by using various kinds of chopping devices. So what you do is make bunches of neutrons and then measure how long it takes them to propagate over a given distance. From that, you get the initial and final velocities. And once you know the initial and final velocities, you can calculate this energy loss. And that's what you cannot do with X-rays. So the reason this is so nice is you have control over both the energy transfer and the momentum transfer, which gives you a lot more information about what's going on in the system. Now, in practice, we don't measure the final state of the target. We just do an experiment and you don't worry about what the final state is. So in order to get this rate, we're going to have to do a sum over all the final states of the target. Also, in practice, we don't determine the initial state of the target. We assume it's in thermal equilibrium. So I'm going to put in another factor. I'm going to do an ensemble average over the initial states. So I put in 1 over z, which is now the partition function, not the charge on the nucleus. And you do a sum on I, e to the minus beta ei. That's using the canonical ensemble to average over all the thermally excited initial states of the system. Now, there's some more factors. If you do this experiment, you have a little detector. And the detector doesn't measure all final states of the neutron. It only measures the ones that go through the little detector. And so we have a function which tells us delta k prime is the sum over all states that lie in these k that are detected. And I'm going to go to an integral which gives you a factor of v over 2 pi cubed in the density of states. So I write this as v over 2 pi cubed. And then I do an integral d3k prime, but they're only over the states involved in delta k prime. So there is a limited final state that we're going to detect. And that turns out to be crucial in doing the kinematics. And finally, I'm going to assume we sum over all the final neutron states, and we average over the initial neutron states. So I get a sum over lambda prime, and I get a factor of 1/2 sum over lambda from the averaging. So there's an extra factor 1/2 sum on lambda prime. From the averaging and the sum over the final neutron states. So you put this all together with this matrix element, and now you apply all these operations. You take the sum over f, 1 over z times the sum over I times this factor. You take this factor, and then you multiply by the allowed final states. And then you end up with a long formula. And I don't want to write it down. This is the transition rate from the average initial state to a particular set of final states And we've summed over all final states of the target, but only those that are kinematically allowed will contribute because of this delta function here. So in fact, it looks like you've done a lot more, but in fact, the delta function restricts yourself. Now, in order to get the cross-section, we know the transition rate per unit time. And I'm going to assume we have 1 neutron per unit volume. So in order to get the cross-section, all I have to do is divide by the incident flux of the neutrons, which is the velocity of the neutron divided by the volume. And then you just do a little kinematics that the velocity of the neutron divided by the volume, you know the velocity because you know the energy. And so the velocity is h bar k over the mass of the neutron. And so this is just h bar k over m sub n times volume. So you have to divide by this factor after you've done all these averaging to this formula. And it's a lot of writing. And so you end up with the following formula for the cross-section, the differential cross-section. So let me write this out because there are a lot of things to go on here. d2 sigma. It's d2 sigma because we have a differential in energy and a differential in momentum. So it's basically a double differential cross-section. Is you get this 2 pi over h bar. You get this overall factor 4 pi a sub s h bar squared over twice the mass of the neutron times the volume squared, because it's square of the matrix element. You get 1/2 sum on lambda lambda prime. You get delta lambda lambda prime from the orthogonality of the neutron states. You get, sorry, there's a lot of writing here, but it's important to do it once. You get sum on f and I over the target states, 1 over z, the partition function, e to the minus beta ei. And now you get a whole lot of other factors. And again, I'm sorry, it's just a lot of writing. This whole thing is now multiplied by f n q adjoint I, absolute value squared. You get the delta function h bar omega minus e f plus e I. And finally, you get this factor v over 2 pi cubed integral d3 k prime over delta k prime. This is over the final states that we're going to detect, m sub n v over h bar k. This is dividing by the incident neutron flux, and I think that's everything. Now, if you check, you'll see that all of the factors of v cancel, which it should. You get a 1 over v squared from the square of the matrix elements. You get a factor of v from this final state. And you get a factor of v from the incident neutron flux. So it's independent of the volume with its box normalization. If it didn't work out that way, it means you've done something wrong. So that's the first thing, is that all factors of v go. They all cancel out, and that's very important. Now I need to do a little computation in order to show you how you get some more steps. It's not hard. So I'm going to assume this integral here is going to be d3 k prime is k prime squared dk prime d omega prime, where this is the solid angle and this is just the usual volume element in three-dimensional spherical coordinates. And I'm going to write this in what looks like an odd way, 1/2 k prime dk prime squared. So this is the differential of k prime squared d omega prime. And k prime squared with a factor of 1/2 is just what comes into the energy. So this is essentially, apart from numerical factors, the differential of h bar omega. Okay? So I can write this now as k prime d omega prime times the differential of h bar omega. And so that's where you get a differential of omega from this factor. And so that's why we get a double differential, because it's a d omega, capital Omega prime. It's the differential of solid angle and the differential of energy. So it's a double differential cross section. That's why we write d2 sigma here. And finally, the other trick I'm going to use, not a trick, you write delta of h bar omega minus e sub f plus e sub I as 1 over h bar delta omega minus ef minus ei divided by h bar. That's the conventional way to write this. So in this delta function, I'm going to write it with a factor as a differential of a delta of omega with a factor of 1 over h bar in front of it. Okay. Now, you just have to go home and write all this down and collect all the factors carefully. And at the end of the day, you get a very simple formula. And this is a conventional way you write it. So I'm going to have to erase something. Let me erase this. And I'll write you the final answer in the following very elegant and simple form. So the final answer is d2 sigma d omega prime. It's a double differential in energy and direction. And it's conventional to put a factor of n in front, a sub s squared, k prime over k, times what I'll call s of q as a vector in omega. So this is just a trivial factor in front, and this is called the dynamic structure factor. Okay? And you put a factor of n here because the idea, if you're scattering from a many-body system, the total differential cross-section be proportional to the number of atoms in the system. And that's just a convention, but it's a very convenient convention. And so all of the information about the target, these are just kinematic factors. They have nothing to do with the target. And everything about the target, everything about the structure of the target is hidden in this dynamic structure factor. So let me write that out for you. And this is something you may have seen. The magic of this is that all the factors of h bar and everything are gone. They all cancel out. That's what you have to go home and check. And all the factors of the mass of the neutron drop out, because everything about the neutron is here and nothing about the neutron is in this except for the q and omega, which is the energy and momentum transferred from the neutron to the target. Okay, so there's just a lot of algebra here. It's tedious, but it's the kind of thing you may have done in graduate courses. If you're interested in seeing this done, Ashcroft, Merman, Appendix N does this out in gory detail. If you want to see this all, this far is all done in Ashcroft and Merman, if you want to look at it and see it done. The rest of what I'm going to do isn't really in Ashcroft and Merman. So S of Q and omega is 1 over capital N, the partition function, sum on F and I, e to the minus beta EI. And now we get the matrix element F N of Q adjoint I squared delta omega minus EF minus EI over h bar. Okay? So this tells you all about the properties of the target. All the details of the neutron, the only ways it comes in is the change in the wave number of the neutron. And this gives you the square of the scattering length. Now, n of q is dimensionless because it's the three-dimensional volume integration of a density. A Fourier transform, the density has the dimensions 1 over length cubed. So n of r has the dimensions of 1 over volume. The integration to get you n of q, the Fourier transform, means that n of q is dimensionless. So this factor is dimensionless. These are all dimensionless, so the dimensions of S of q and omega is 1 over omega because of the delta function. So this has the dimensions 1 over frequency. Okay? And that's, I mean, this is just a conventional, but this is what this is what you see if you look in all the books. You can interpret this physically as if the neutron transfers wave number q to the target, what is the relative probability that it also transfers energy omega, or h bar omega? So you can think of it as a conditional probability. You determine by your kinematics the change in k to k prime, or you determine q by where you put your detector. And you move your detector around in space, you vary q within limits, and then you measure the frequency dependence of all the different neutrons, and what you do is sometimes you'll get sharp peaks. And it's the position of those sharp peaks and how they vary with q that's of such interest. So let me say a little bit about why this is important. Question?
What about the momentum of the target? Like, suppose I do a scattering, neutron scattering from a superfluid at final temperature.
You assume it, I'm assuming it's a macroscopic sample, so the recoil of the whole sample is irrelevant.
But what about each nuclei?
Well, the important point is because it's a many-body system, you find that there are certain collective modes. And it's these collective modes that are called quasi-particles, that they're what you're studying. You're studying the excitation of quasi-particles. Think of the simplest famous example is a macroscopic crystal. Say a crystal of argon. It could be anything. Let's take a simple monatomic crystal, dielectric crystal that's not conducting. You know that, I mean, think back to your one-dimensional example of a crystal lattice, a one-dimensional lattice. You have atoms along a line. There are springs between them, say spring constants, whatever you want to call them. Now, you can write down your Hamiltonian in terms of the sum of p squared over 2m for each nucleus and the interaction between them. But you don't think of the problem that way. You do a canonical transformation by looking at the normal modes of the system. Because it's a quadratic Hamiltonian, you can diagonalize it exactly, and you end up with a set of normal modes. And you do a canonical transformation, so the Hamiltonian is exactly the same as a sum over all normal modes with some associated energy. And therefore, you think of a crystal not as an assembly of atoms. It's much more useful to think of it as an assembly of potentially excitable normal modes. And the normal modes are labeled by Q. So if you excite the crystal by giving it momentum Q, which you determine by the angle between the initial and final neutron, then what you end up with is you measure the energy. And in the harmonic approximation, the only allowed energy will be the energy associated with that particular normal mode. Now, at long wavelengths, you can just think of those as elastic media. And so in an elastic medium in one dimension, you just get a normal mode which has the sort of classic spectrum. It'll look like this. This is omega. This will be Q. At long wavelengths in one dimension, you get a linear spectrum. Omega is some speed of sound times q. And if q times a is much less than 1, then you just get this linear behavior. Now, as you go on to higher wavelengths, shorter wavelengths, it bends over, and you get to the Brillouin zone boundary, and then it's formally periodic and comes back down like that. So it's flat at QA is something like pi over 2, call this QA, but it's linear out here. Now, you really don't have one-dimensional crystals, but we do have three-dimensional crystals. And so if you do this with a three-dimensional crystal, you end up with, you have the elastic picture tells you have a longitudinal mode and two transverse modes. And depending on the symmetry and the direction, these two transverse modes may be distinct or they may be degenerate. And so if you do the picture for a three-dimensional crystal, what you get is a mode that looks like this. This will be the longitudinal, and you get a mode that looks like this, which will be the transverse. And depending on the splitting, you may get two of these transverse modes or not. And so what you do, if you look at the energy S of q and omega for a fixed q, you get a big peak at the transverse mode, you get a big peak at the longitudinal mode, and then if you vary the q, these shift, and that's how you map out these curves. So these are how you map out the phonon spectra of solids. And there's a whole chapter in Ashcroft and Merman that talks about all that. So it's a very good source, and they have nice pictures of various kind of crystals. Now, most crystals like sodium chlorine have more complicated things because in addition to the acoustic branches, you have optical branches where the two different atoms move against each other, and these are high frequencies. So you can also measure those with neutron scattering. So it's very powerful. And then you just have to use your group theory and other kinds of stuff to figure out what's going on. So this has been a very powerful way of learning about the properties of crystals. And the crucial idea is that you don't think of it as a set of single atoms, but because it's an interacting many-body system. This is Landau's great idea, the Landau quasi-particle, that you can describe a very complicated many-body system in some good approximation in terms of a set of effectively non-interacting quasi-particles. Now, that's not obvious, but it's true and very powerful and very important. Okay? So are there any, I mean, I'm sure you've heard about this in various contexts, but I just want to make sure, I thought it was good to talk about this. Are there any questions about this? Because you can do this now for liquid helium as well. Liquid helium, because it's a liquid, doesn't have transverse modes. So in liquid helium, you only get a longitudinal mode. And this is the famous Feynman-Landau phonon-roton spectrum, and I'll either talk about that later today or I'll talk about it next time, depending on how far we get. Okay. So this is the end result of a lot of work, namely the formula for S of q and omega. And it's a complicated function of two variables, q and omega. Now, we can think of various ways of treating this. Suppose we don't measure the final neutron energy. Suppose we turn off the resolution of measuring neutron energies, so we just measure S of q, but we integrate over all omega. So let's look at that just for fun. I'm going to do a whole lot of manipulations on S of q and omega, but let's just for the fun start with this one. Is there a better, I don't know, can we get a better marker? Because these are all sort of running out. Suppose we don't measure omega. In that case, what we measure is the integral. Well, it's really the integral from minus infinity to plus infinity d omega S of q and omega. And let's ask what this quantity is. So let's imagine we just do this integral. This is the simplest kind of thing you could imagine. So if we do this, we get 1 over nz. We get sum on I and f e to the minus beta ei. We get this matrix elements, thank you, f n adjoint of q I squared. And now the integral over omega of this delta function is just 1. And since we integrate from overall frequencies, whatever the value of EF minus EI is, there's always going to be some omega that counts. So this is the answer because the integral just eats up the delta function. Okay? And now we can do some pretty tricks here. So let me write this out. And I'm going to leave this formula. If I'd been clever, I'd have had it up here. So I'm going to come down here. I don't want to write this whole thing out again. So I get 1 over nz, sum on f and I. e to the minus beta ei. Now let me write this matrix element out. I get I n of q f times f n of q adjoint I. And these are strictly vectors, although in many cases this only depends on the magnitude of q because of rotational invariance. And that's the answer. Almost. Now we can play two very pretty tricks. The only f dependence is here. In this formula, f appears here, but because we've eaten up the delta function, the only f dependence is here, and we know how to do the sum of f adjoint f as states. This is just the completeness relation. So the sum on f just gobbles up these two projections. Is that clear? And so I can write this now as 1 over n z sum on I e to the minus beta ei times I n of q adjoint I. But this is exactly what we would call the thermal average of these two operators, because it's just the ensemble average. And so at the end of the day, this integral here is exactly 1 over n times the ensemble average of n of q adjoint ensemble average. So this shows you in detail what I meant last time when I talked about an ensemble average. And this is what you measure with X-ray scattering. Because I was treating them as classical operators. Here I'm calling them quantum, and instead of calling it a complex conjugate, I call it an adjoint. But it's just the way you go from classical to quantum physics. And so this, and I think I gave the wrong definition, this is what you call S of Q. This is the X-ray structure factor, the static structure factor, because you've integrated over frequencies. So you get the very nice result that this is what you measure in neutron scattering. And if you integrate over all frequencies, you end up with the X-ray scattering. I think before I wrote little n, if you look at the dimensions, this is dimensionless, and this has dimensions 1 over omega, so this integral is dimensionless. And it has a factor of 1 over the total number of atoms, not 1 over the density. But this is the conventional. So this makes a connection between neutron scattering, which has a lot of information, with X-ray scattering, which has less information, but still has the Q information. Okay? So that's the first really pretty property about what you can do with S of Q and omega. So as I say, this relates X-ray scattering to neutron. Okay? But now, because this is a much richer function, there's a lot more information in this. And so I'm now going to do some other interesting and important manipulations on this. So let me erase this. I mean, a lot of these are just tricks, but they're very powerful tricks. It's often convenient to write the delta function as a Fourier integral. So I'm going to write delta, formally just delta omega, as 1 over 2 pi integral d omega from minus infinity, integral of t dt e to the I omega t. Okay? So this delta function is going to be a Fourier integral over time with omega minus the difference of the two energies divided by h bar. Okay? And this is a formal manipulation, but it turns out to be very powerful. It's a standard manipulation that's going to lead us to the Heisenberg operators. So this is how you get the time dependence in these operators. Okay? This is not an Ashcroft and Merman. Where would it be? It must be in these books of Pines and Noziere, but I didn't go back and check. If you're looking for references, I can suggest some. But I mean, these are just tricks that theorists learn over the years. And if you look at books about S of Q, books on neutron scattering, they would cover all this. So I'm going to erase this. And again, unfortunately, this formula. So S of Q and omega is 1 over 2 pi n z. How do I want to write this? You get an integral dt. Sum on f and I, e to the minus beta ei, I n q f, f n q adjoint I. And now it's convenient to recognize that if Q is non-zero, this really means this is only the fluctuation part. So I'm going to put the tildes on here to mean this is the fluctuation part, because the spatial average is uniform, and that the Fourier transform of the average only contributes to Q equals 0. So only the fluctuation part enters if Q is non-zero here. Okay? So n tilde of Q is the fluctuating part, because that's the only physically relevant part. And now I get this exponential of IT times omega minus EF minus EI over H bar, like that. So this is I get the factor of e to the IT omega. Then I get this factor of e to the IT. Well, let me now notice something. Notice that e to the I, e sub I minus e sub f times t over h bar times I n tilde of q f. I can write this by putting this factor associated with this and this part associated with this factor by writing it in terms of putting the exact Hamiltonian. These are the exact many-body energies of initial and final states of the many-body system. So I can write this as I e to the I h t over h bar n tilde of q e to the minus I h t over h bar f. Okay? Because this Hamiltonian acts on this state to give you this factor. This Hamiltonian acts on this state to give you this factor. But now we have a matrix element between I and f of this is what's called a Heisenberg operator. And so this is exactly the same as n tilde of q in time interpreted as Heisenberg operator. So let me write that down. That this factor e to the I h t over h bar times any operator times e to the minus I h t over h bar is what we call O sub t as a Heisenberg operator. That's the usual formalism in quantum mechanics. And so by this device, we have gone from these functions of q only to a time-dependent density fluctuation n tilde of q and t as a Heisenberg operator. Is that clear? Because we have this structure e to the IHT, e to the minus IHT with the operator sandwiched in between. And so at the end of the day, we get, question?
It takes a whole day.
Well, I know, this is a lot of work.
Always at the end of the day.
Well, no, somebody, I don't know who figured this out. You can see that's why S of Q and omega is so interesting. because it's absolutely full of interesting and useful and important information. So I'm going to erase this because it's just, I'll have to write it again, but it's just too confusing to leave it in the middle of the board, I think. So now I can write this as S of Q and omega as 1 over 2 pi n z, integral minus infinity to plus infinity dt, sum on f and I, e to the minus beta ei. Now I get I n tilde Heisenberg of q and t, f. Here, let me try one of these new ones. Now I get f, and I can call this nh adjoint of q and 0, because time t equals 0, they're the same as the Schrodinger representation, I. And I think that's everything. Right. And now, the magic of going to these Heisenberg operators is the only f dependence is here. So once again, I can use completeness. And that's the f has disappeared in the time dependence of this. So the fact that this is a time-dependent Heisenberg operator means I can eliminate this sum over f just by using completeness. And so let me see if I want to write it out. OK, just to be very careful, 1 over 2 pi n z, integral minus infinity to plus infinity dt, sum on I, e to the minus beta ei, I, n tilde h of q and t, and h tilde adjoint of q and 0, I. And this is just the ensemble average of these two operators with a thermal ensemble. And so finally, the whole point of this is at the end of the day, I can rewrite my original expression in the following form. And this is the final answer that's so interesting, that S of Q and omega is 1 over 2 pi n, integral minus, there's a factor of e to the I omega t, and that's crucial. I get dt e to the I omega t times the ensemble average nh tilde of q and t, nh tilde of q and 0 adjoint. And so S of q and omega, which you measure by neutron scattering, is exactly the time Fourier transform of two Heisenberg operators at different times. So this is how you get time-dependent functions. It's because you have the omega information that you get from the neutron scattering that you don't get from X-ray scattering, that you can take this, you can interpret this as a Fourier transform of two time-dependent operators at different times. Now, Heisenberg operators at different times don't commute. And so it's crucial that you're talking about things at different times rather than the same time. Okay? And now we eventually will make, next time I hope to make connection with the many-body formalism. In the many-body formalism, you study what are called Green's functions, which are time-ordered products of two Heisenberg operators at different times. And there's a trick that takes you from a time-ordered product to a product like this, which is, this is not a commutator, but this is just a single product. But there are tricks that allow you, using complex variable information and causality, that you can calculate. In various approximations, you can calculate this. Okay? But it's crucial that this is time t and this is time 0. And if you remember, because of the q, we can write this, assuming this is a translationally invariant system, we can also write this as an integral dv over 2 pi cubed e to, well,
Yeah, e to the I k r.
e to the minus I q dot r times nh of r and t nh of 0, 0. So you get this ensemble average of the, assuming this is translationally invariant, it only depends on one is at the origin, one's at time t in position r. So this is a four-dimensional Fourier transform of this function. Okay, and so you end up with these correlation functions of Heisenberg operators, in this case density fluctuations at different times. Okay? There's some other important properties of S of Q and omega. Do you want me to spend 10 more minutes talking about that? Or should I? I won't get to the Feynman stuff, but we can do that next time. I decided it doesn't matter how much you cover, I'd rather do it carefully so you can understand it. Now, the other things we're going to do are basically tricks, but they're famous and important tricks. So it's, again, more ways of manipulating S of Q and omega. And so there's a lot of, this is just math, if you like, but it's elegant math, and it gives you results that are useful. So I wanted to go through this result just because it shows you how these correlation functions of two Heisenberg operators at different space-time points naturally arise just because of the properties of translationally invariant systems. And it makes you realize why studying a dilute Bose gas in a trap is vastly more complicated because you don't have translational invariance. You have time translational invariance, but you don't have space translational invariance. And so most of these, some of these tricks are much more complicated. And that's just the fact of life. So let me erase this and start again. Let me write this definition in the original form, just so you can see how this all works. The first thing I want to derive is something called detailed balance, which talks about the difference between what's called Stokes process and anti-Stokes process, which you may have come across in other contexts. So I think question.
Yeah. Since you are working with NQ, which is the fluctuation part, wouldn't it be better to work with interaction picture instead of the Heisenberg? Because I think it's only the interaction part of the Hamiltonian that will make the N evolve in time, right?
I'd have to think about it. Later on, I'm going to do some manipulations which depend on the fact that the Heisenberg, the Hamiltonian written in position in first quantized form is just the sum of the kinetic energies plus the sum of the interaction energies. And it turns out the kinetic energy part is the crucial part for the manipulations we're going to give. I'd have to think about it. I haven't.
Because then you could set up a perturbation.
Well, I'm going to do that next time when I talk about linear response. Okay? But I haven't thought about it in this context, so you may be right. So I'm going to now write S of Q and minus omega This is just using the definition we've had. Or let me call it minus Q. I want to ask, this is time reversal invariance or symmetry. I imagine I study S for minus omega and minus Q. Okay? And I'm going to use the fact that N tilde adjoint of Q is N tilde of minus Q. So now I'm just going to use my definitions to write this all out. I get 1 over N Z sum on F and I, e to the minus beta EI. Now I get F N tilde of Q I squared. And I'm using this property to write this as N of minus Q. And since I've changed the sign of Q, I just get N of Q here because of the actual minus sign. And then I get a delta function, which is minus omega minus EF minus EI over H bar. Okay? So this is just writing out the original definition but putting in minus signs, which take you this factor here and the minus omega here. Now I notice that I'm summing over all f and I. F and I are what I call dummy variables. They're just labels. And so I can interchange I and F. So I'm just going to, everywhere I have I, I'm going to write F, and everywhere I have F, I'm going to write I. So I can write this now as 1 over NZ, sum on I and F, and it doesn't matter because I'm summing independently which order I write these in. I get e to the minus beta EF now. I get I n tilde of Q. This quantity here has to be 0. Otherwise, it's going to not work. And so I need omega is equal to EF minus EI over H bar, because otherwise this delta function is 0. This is minus omega plus EF minus EI, and so that's why I get this factor here. And so I can replace this, so EF is H bar omega plus EI, okay? And so I can write e to the minus beta EF as e to the minus beta H bar omega times e to the minus beta EI. And so doing this manipulation, what I end up with is S of minus Q minus omega is equal to 1 over NZ, sum on F and I, e to the minus beta EI, e to the minus beta H bar omega, times this sum, I n of Q adjoint I, that's because I've interchanged. Let's see, when I interchange this, what went wrong? Oh, it's this, F. No, this is, well, I want F n QI squared. And now I get a delta function. This is even, so I can write this as delta omega minus EF minus EI over H bar. And now this factor, apart from this thing, is just the original S of Q and omega. So you'll have to go home and check. But the final result, which has a very simple interpretation, is that S a minus Q minus omega is e to the minus beta H bar omega S of Q and omega. And this is called detailed balance. There is a relation between S for a particular Q and omega and S for the same opposite Q and negative omega. Now S, this has a simple physical interpretation. This is called detailed balance. Suppose we have an isotropic system. If it's isotropic, only the absolute value of Q enters. And so this is just equal to the absolute value of minus Q, which is the same as the absolute value of Q. So basically, writing it in scalars, we say S of Q minus omega is equal to e to the minus beta H bar omega S of Q and omega. Now, we think of this as the probability that if you transfer magnitude momentum Q, the neutron also transfers momentum omega to the system. Now, if omega is positive, the neutron gives up energy. It creates an excitation in the system. That can happen at 0 temperature. because you can always create a quasi-particle in the system. Okay? Now, S of q and minus omega is the probability that the neutron absorbs energy h bar omega. And that can only happen if you already have a thermally excited quasi-particle in the system. And so at very low temperature, the probability of that happening is very small. When the neutron creates an excitation, it's what's called a Stokes process, because it creates an excitation. The Stokes process can occur at 0 temperature. The anti-Stokes process, where the neutron absorbs energy, can only happen at finite temperature, because otherwise there's no thermal quasi-particle for the neutron to interact with and absorb its energy. And so that's why this becomes exponentially small compared to this at low temperature, when beta goes to infinity. So this shows you why the signs work out the way they do. The anti-Stokes process at high temperature is equally probable with the Stokes process. But at low temperature, the anti-Stokes process is essentially impossible to happen. And so you just end up with only, if you look at the spectrum of the neutron scattering for fixed q, at high temperature you get an anti-Stokes peak and a Stokes peak. But at low temperature, the anti-Stokes peak is gone or very small, and so you get a very asymmetric structure. You have a big peak on the positive omega side, where the neutron loses energy, and a very small peak for the neutron absorbing energy, because there are no quasi-particles to interact with. Okay? So that's, I mean, the physics of this is very clear, I think, and the manipulation is a little tedious, but this final answer is, I think, pretty easily interpreted in terms of the difference between the creation and absorption of a particle. Okay? Let me do one more thing and then I'll stop, because there's one more important property of S of q and omega. It's called the F sum rule. And it's an exact property of S of q and omega. And if you make a theoretical model for S of q and omega, unless it satisfies this exact sum rule, your model won't probably be very useful. Okay? So I'm not going to do all the algebra here because it gets a little tedious, but let me start and show you how it goes, because this, again, is a very important thing in all sorts of models of interacting many-body systems. So this is called the F sum rule. It goes back into atomic physics probably from 1926 or 27, where F was used for the oscillator strengths. And I don't know the history of it. But in this case, it's a moment, the first moment of S of q and omega. And so what we want to study is the integral from minus infinity to plus infinity d omega. I'm going to put in an extra factor omega to make it the first moment, S of q and omega. Okay? So let me write this out. 1 over n z sum on f and I, e to the minus beta ei, f n adjoint of q I squared, integral minus infinity to plus infinity d omega, omega, delta omega minus ef minus ei over h bar. Now, this integral I can do because of the delta function, and I set omega equal to the difference of the energies divided by h bar. So this just gives me 1 over nz sum on f and I, e to the minus beta ei, f and tilde of q adjoint I quantity squared times ef minus ei over h bar. Okay? So I get the difference of the two energies with this quantity. And now, if you just go home and write it out, you can write this whole thing as a double commutator of these operators. And I'm not going to try to prove it, but you can go home and check that the integral minus infinity to plus infinity d omega omega s of q and omega is equal to 1 over 2 n h bar n tilde of q commutator with the full many-body Hamiltonian commutator with n adjoint tilde of q. So you compute this commutator, then you compute the commutator of this commutator with this. So it's a double commutator, and it's an ensemble average. Once you've done this manipulation, you can use completeness to eliminate the sum over f. And then you have an ensemble average, so you do the sum over I, and that gives you the angular brackets. Okay? Now, this looks awful. But in fact, this is where you come back to this structure that H, written in terms of T plus V, and T is the kinetic energy at sum on I minus h bar squared del I squared over twice the mass of the whatever particle you're talking about. This is the many-body particle. And V is just sum on I and j prime, I not equal j of little vij. It's just a two-particle interaction because I'm assuming translational invariance. Now the beauty is that n of q, or n tilde of q, is a function of r. And so that commutes with v. So the v plays no role in this commutation relation. So the commutator of h with the density fluctuation operator comes from this piece. And so you get this Laplacian acting on, remember that n of q is basically sum on I e to the minus I q dot ri. Okay? And so this gradient acts on this. And you can work this out. It takes about a page of writing. It's pretty straightforward. And at the end of the day, you get a very simple answer, which is called the famous F sum rule. And so after a lot of work, you end up with the integral minus infinity to plus infinity d omega, omega s of q and omega. This is just the first moment of s of q and omega. And the answer is h bar q squared over 2m. So that's the beautiful answer. And this has to be true for any s of q and omega. If you fix q and integrate over omega times omega, you get this answer, h bar q squared. And as you vary q, you have to get the right q here. It's a very restrictive sum rule. Most simple-minded models that you write down for s of q and omega fail this test. So you see we now have two important results for the s of q and omega. The first result, well, we have lots of results. The first result is the zero moment. The integral of s of q and omega over omega is just s of q, the static structure factor measured in X-rays. The first moment is this F sum rule, which is very restrictive. I showed you this representation in terms of Fourier transforms of Heisenberg operators at different space-time points, which is conceptually very important, although you use it mostly for computations. And finally, I showed you this detailed balance that says that S of q and omega is more probable than S of q and minus omega because of the Stokes and anti-Stokes process. So S of q and omega, it looks complicated. It is complicated. But it's got a huge amount of information in physics about the many-body system. And one of the goals of many-body physics is to try to compute models for S of q and omega that satisfy all these different requirements. And that's not a trivial thing. And we'll talk a little bit about some of that next time. But I may end up leaking over into the, you can tell me whether you want me to finish that the following time, or whether you'd rather I just go on and start talking about the dilute Bose gas. I mean, the technicalities of the manipulation of the many-body states get to be a little intricate, and you may decide you'd rather I just go on and talk about the dilute Bose gas, which is probably more review for many of you. So anyway, I'll stop here, and I do want to, next time I'll start by talking about these Feynman models, because it's a very pretty physics, and it involves liquid helium, and it's something that you may not have come across. So let me stop here. That's an hour and a quarter, which is enough for any person. And of course, I'm happy to answer questions.
Hello. Maybe a stupid question.
There are no stupid questions.
I understand the rule of the temperature for the Stokes and Stokes. Especially if I think in phonons and crystals, I can get very straight there. Now, let's go to a superfluid. And then I'm making a scattering, neutral scattering. And if I am in zero, I understand I have no excitations on there. But in any final temperature, you are telling me that I always have a population of excitation.
Well, at very low temperature, the number of phonons is very small. It's basically the same rule as a crystal.
Let's forget about the phonons. Let's take another excitation.
Well, the only other excitations are the phonons and the protons in liquid helium. I mean, the spectrum.
I thought that you could have some collective modes and everything.
I think the collective.
That if I go to the trapped atoms.
Oh, the trapped atoms. Oh, that's a much more complicated system. I was thinking of helium, where you have a bulk helium. Yeah, I mean, in a trap.
Oh, in a bulk of helium, I don't have some of the modes. But let's imagine this sample of atoms. If I'm in final temperature, it's right to think that I always have some population of some of the.
Yeah, the collective modes, the breathing monopole mode and the quadrupole mode, presumably at finite temperature they're excited, but because the modes in a finite system are discrete, you get e to the minus beta times the energy of these modes. And so at low temperature, these thermal factors are frozen out. What I don't know is whether 50 nanodegrees is low temperature. I haven't put in the numbers recently.
It's low temperature.
I would have thought it's low temperature.
Yeah, but even though it's a temperature that's higher than the energy of those modes.
No, I mean
Those modes are higher energy.
They are higher.
Yeah, they're higher.
the breathing modes.
There's nothing there.
Right. If you're cold enough,
So
there
it's
won't be any motion.
and what is cold enough? 100 nanodegrees?
Well, it sort of depends on your
It depends on the
It's
size of the
H
trap.
H bar omega, so it's whatever. Where omega is the harmonic oscillator. So it's whatever your trap is.
Yeah, but like the quadrupole mode would be compatible to the energy, to the h bar omega of the trap.
Right.
Right, but it's the
But
question
your
is
temperature can be colder.
your temperature can
Yeah,
be
but
colder.
Not much colder than that.
Right. If you're comparable, then yeah, you'll have some finite
Below the
oscillation.
critical temperature, then I should have some excitation.
But they would be smaller by Boltzmann factors than the other one. I mean, I don't know whether that was an important factor in the early, I mean, Debbie Jin's group and Wolfgang Ketterle's group back now more than 10 years ago did very detailed studies of these collective modes. That was one of the things that persuaded the skeptical theorists that the Gross-Pedievsky equation actually made sense. I mean, it seemed too good to be true that this very simple theory would actually describe these real systems. But when you predicted the collective mode frequencies at the 1 or 2% level, and the experimentalists did them, and by God, they were the same. They were very impressed, particularly because there were some detailed factors involving the anisotropy. If you had a long cigar-shaped trap, the behavior was different from if you had a nearly spherical trap. And you got the m equals 0 breathing mode. You got the, I guess, the plus or minus 2 quadrupole modes. Those were the ones that I remember. And I guess there's an angular momentum 2 breathing mode, an m equals 0, L equals 2 mode. And I don't remember whether they studied that as well. I remember the pictures. They're all in this review article by Dalfovo and Pedievsky and Sandro Stringari back in 99 from RevMod Phys. And they're in the books. I mean, Chris Pethick's book has them. And Pedievsky and Stringari has pictures of all these collective modes. I don't know. I don't remember whether they talk about the finite temperature effects. But the finite temperature effects would be just this kind of detailed balance that you would have thermal factors.
I think the calculation of Stringer is 0 temperature.
He's always 0 temperature. But once you've got the modes, typically the mode frequencies don't change at low temperature as long as you don't go to too high temperatures. And so you can just take the 0 temperature frequencies, and put them in to calculate the thermal factors. And certainly for clarity experimentally, you would try to go to a regime where the thermal factors are small, but they're probably not negligible. And when you look at what's called the critical velocity in liquid helium, if you imagine sending a small impurity through the fluid, you imagine you're at 0 temperature, and you say the only thing that can happen is the impurity can't lose energy until it's kinematically favorable to create a quasi-particle. And that gives you the critical velocity, which in liquid helium, if you ignore the roton, it's just the speed of sound. It's actually smaller than that by a factor of 4 because of the roton, roughly. But I don't want to go into all that because it's not really, this is not really about liquid helium. Okay, other questions? It's good questions. I'm happy to answer them.
So at the beginning, you assume the delta function as the interaction between the neutrons and the nucleus.
Right.
So my question is, how general are these expressions for different systems?
I think as long as you put in the correct scattering length, which is basically just an overall factor, I think they're in a sense exact. The one approximation we did make was the assumption that the interaction is spin independent.
Right.
Now there must be examples of certain nuclei. I mean, the helium nucleus is nice because it's an alpha particle which is spin 0. It doesn't have any angular momentum. But if you take different isotopes that have higher spin 1/2 or spin 1 or spin 3/2, then in general, I'm not an expert in nuclear physics, but I would anticipate that you would get spin dependence. And so you have to think about the spin dependence. You don't have this Kronecker delta that tells you that the final neutron spinner just works directly on the initial neutron spinner, but you'd have some spin-dependent interactions. And the usual model for spin-dependent interactions is it's sigma of the neutron, the spin of the neutron, which is a 2x2 Pauli matrix, dotted in to the spin of the nucleus. So you get a sigma dot S, which you then, and if S is 0 as an alpha particle, helium, then you just get the Kronecker delta. But otherwise, you have to work out these spinor matrix elements, and you end up with answers that depend on the spin of the nucleus. And then you would assume, presumably, that you don't measure the spin of the nucleus unless you have a polarized nucleus. So you average over all the states of S. And what I don't know is you may end up with the same thing as if it's spin independent. I don't know, because I haven't done that calculation. But certainly if you have a nucleus in a very strong magnetic field, or you use circularly polarized light to polarize the nucleus, then you have to go through all these Clebsch-Gordon coefficients to figure out what these actual answers are, and that's probably complicated. I mean, lots of people must have done it. I just haven't. I mean, at SLAC, where I work at Stanford, there was a big project to study electron scattering from polarized targets. And the best thing they found, you couldn't get big enough magnetic fields to get much polarization, but by using intense circularly polarized laser beams and tricks, they could create significant 70 or 80% polarized nuclei. And then the electron scattering from the polarized nuclei was different from the electron scattering from non-polarized nuclei. Electron scattering through the Coulomb interaction interacts with the nucleus. You can focus on that because you get a large Z. I mean, again, I don't know how they do it, but I know they can do it. And so because of that, apart from factors that involve E squared over Q squared from the Fourier transform of the Coulomb potential, you end up with also S of Q and omega. So electron scattering off a target can also measure S of Q and omega. And so that's another application. I didn't want to get into that, but for the nuclear physicists, they all know about S of Q and omega through electron scattering, even if they don't do neutron scattering. And the other comment is there is an analog involving spins where you get a spin S of Q and omega. Instead of having the density fluctuations, you have the spin fluctuations. And because the neutrons not only interact with the nucleus, but the spin of the neutron interacts with the spin of the nucleus. So if you're very careful, you can disentangle the density effect from the spin effect. It's hard, but I know it's been done. And so there is an analogous spin S of q and omega, which has exactly the same properties, except this would be the spin density fluctuation. And so that's very interesting in studying what are called spin waves. Instead of studying density waves, you can study the spin waves in a magnetic system. And that's why you do neutron scattering off high TC superconductors. You study the spin structure because of you have to disentangle the spin and density fluctuations. But it can be done. It's hard experimentally, but it's very important. Okay, other questions? Good questions. No? Okay, well, I'm happy to talk to you about it if you'd like.